Hello and welcome to the Scientific Adventures of Beardman. Today we're going to take a deeper look at the nature of light. Remember how we just studied Young's double slit experiment from 1801? That amazing experiment where light passed through two tiny slits and created an interference pattern on the screen. That was a total game changer because it convinced everyone that light was a wave. But hold on tight because things are about to get even more interesting. We're going to dive into another mind-blowing phenomenon called the photoelectric effect, which will make us question everything we thought we knew about light. Have you ever wondered how solar panels turn sunlight into electricity? Or how automatic doors know when someone is approaching? Well, the answer lies in the photoelectric effect. From the late 1800s to the early 1900s, scientists were puzzled by this effect. They observed in 1887 that when light was shown on a metal surface, electrons were emitted from the surface. Everyone expected energy from light to be able to give electrons enough energy to escape the atoms they were attached to. Yet the existing models of light as a wave could not fully explain the details of this behavior. To help you visualize this, let's head over to Physics Classroom's Photoelectric Effect Interactive. This interactive simulation allows you to experiment with the photoelectric effect and see how it works firsthand. First, let's understand what's going on here. We have a source of light, represented by the flashlight here, which is shining green light with a wavelength of 500 nanometers on a piece of sodium metal. This is causing electrons to pop off the metal atoms. There is a voltage source currently set to 0.3 volts, which is pushing the electrons back onto the metal. Go ahead and change the voltage source to 0 volts. Notice we can also change the frequency of the light being produced. Change the wavelength to 700 nanometers. You should see red light being emitted from the light source. What else changed when you changed the wavelength of the light? This is what baffled everyone for decades. We know red light has less energy than green. Longer wavelength means lower frequency. But if light is a wave, then it should have just taken a bit longer for the electron to absorb enough energy to pop off its atom in the metal plate. But as you can see in the simulation, the electrons never pop off the atom of the metal when there's red light of 700 nanometers. This was screaming to the scientists in the late 1800s and early 1900s that something was wrong with our understanding of light. Let's analyze a little more and see what's going on. Next, increase the intensity. This will turn the light from dim to bright. Sounds like more energy. Can you give the light enough energy to pop off an electron? Go ahead and change the wavelength to 600 nanometers. Now, again, increase and decrease the intensity, the brightness. Can you give the light enough energy to pop electrons off the metal? We have tried changing the intensity and found that it has no impact on creating the photoelectric effect, the popping off of electrons. So now let's try changing the frequency. Make sure you're still using sodium metal and set the intensity to 100%. Now, decrease the wavelength slowly until you see electrons popping off. What wavelength does this occur at? Leave the wavelength at 500 nanometers and try decreasing the intensity. Are you able to get rid of the photoelectric effect? test other wavelengths. Which wavelengths cause the electrons to pop off the sodium metal? Now that I have stepped you through some tests, it's time to come to a conclusion. Identify the following statement as true or false. The photoelectric effect is more likely to occur at 550 nanometers and an intensity of 100% than it is at 450 nanometers and an intensity of 5%. At this point, it should be clear that metals have a certain wavelength above which the photoelectric effect cannot occur. We now know that the wavelength is somewhere between 500 nanometers and 550 nanometers. We know that because no matter how much energy from intensity we put into the 550 nanometer light, electrons never pop off the metal. The wavelength that is the first wavelength at which electrons pop off is called the threshold wavelength. But if light is a wave, wouldn't it just keep absorbing from cycle after cycle of the wave hitting it until the electrons had enough energy to pop off? And why would it matter what the wavelength is? Shouldn't more intense light, which is carrying more energy, be able to pop off electrons? In order to answer this dilemma, it took one of the greatest scientific minds ever to live. In 1905, Albert Einstein hypothesized a brilliant solution that still makes sense today. He decided that light must be a particle and a wave, kind of particle wave called photons. Each photon is a packet of energy. And his idea was that when a photon, a packet of energy, hit the electron, if it had enough energy to remove an electron, then the electron would be able to pop off. If the photon didn't have enough energy to eject the electron, then the photon is reflected or absorbed, causing an increased vibrational state. In other words, their energy becomes thermal energy. If the photon had the exact amount of energy that it took to remove the electron, then the electron would have zero kinetic energy after it broke away and would likely become attracted back to the atom that it came from unless there was a voltage drawing it away from the metal. However, if the photon had more energy than was required to remove the electron, the rest of the energy would become kinetic energy of the electron, speeding it away from the metal. Not only that, but since the light can penetrate a few layers of the metal, some of the electrons would be ejected from the surface and therefore have the maximum kinetic energy, but other electrons would lose some of their energy as they worked their way through the layers of atoms above them. Let's take a moment to look at this in the simulation. First, experiment a little bit to see if you can answer the following question. As the wavelength decreases, while below the threshold wavelength, the maximum kinetic energy value increases, decreases, or remains unchanged. Hopefully you noticed that as the wavelength decreases, the maximum kinetic energy increases. This tells us that photons of lower wavelength have more energy. You can see more about the exact relationship between a photon's wavelength and their frequency and their energy in this video. Determining the maximum kinetic energy can be challenging by watching the electrons, especially because scientists can't actually see the electrons like we can in the simulation. Therefore, scientists discovered a way to test for this. It is finally time to play with the voltage slider. By using voltage to push the electrons, negative charges, back onto the metal, we can see how much voltage is necessary to keep the electrons from reaching the wire attached to the ammeter. The harder we have to push with a greater voltage, the greater the maximum kinetic energy of the electrons. Play with this feature a little. How much voltage do you have to apply to stop 400 nanometer light hitting sodium metal from having enough energy to create a current? If you have looked carefully, you saw that at 0.7 volts, there would occasionally be an electron with enough energy to reach the ammeter. This means that 0.7 volts was not enough to stop the electrons with maximum kinetic energy. But 0.8 volts stopped the current completely. So the stopping voltage for 400 nanometer light on sodium metal is between 0.7 volts and 0.8 volts. Mathematically, that could be used to determine the maximum kinetic energy. Now let's experiment with the intensity. What immediately do you notice when you change the intensity from 5% up to 100%? That's right, you see more dots leaving the flashlight. These dots each represent one photon. What happens when those photons reach the metal? That's right, an ammeter reads electric current, which tells us more electrons are being removed from the metal. Did you notice that each photon ejects one electron? While that might not be completely true, that one photon ejects one electron, it is certainly true that each electron ejected is ejected because one photon gave it all of its energy. Now that you know that the dots leaving the flashlight are photons and the dots leaving the metal are electrons, take a moment to look back through various colors, wavelengths of light, and see the effect that each of your dials make. See if you can determine the threshold wavelength of magnesium and the maximum kinetic energy for various colors of light. Can you determine the threshold wavelength of the unknown metal? So there you have it. The photoelectric effect is a fascinating phenomenon that has revolutionized our understanding of light and matter. It has led to the development of many important technologies, such as solar panels, photomultipliers, and light sensors. I hope you enjoyed this scientific adventure with me. We'll catch you the next time on the scientific adventures of Beardman. Until then, keep those brains buzzing and those beards bushy.